Our story begins deep beneath your feet, 100 to 200 kilometers down in Earth's mantle. Here, rock exists in a special state. Not quite solid, not quite liquid. At 1,200 to 1,400 degrees Celsius, the rock flows like honey, moving just centimeters per year in great, lazy currents driven by heat from Earth's 5,000-degree core. As mantle rock slowly rises, pressure decreases, and something magical happens. Minerals begin to melt, creating pockets of liquid stone called magma. This magma is less dense than surrounding rock, so it rises, collecting more melted material and dissolved gases, water vapor, carbon dioxide, and sulfur dioxide. The journey upward is patient. Magma flows through tiny cracks, sometimes pooling in chambers several kilometers across where it rests for thousands of years. In these chambers, temperatures range from 700 to 1,300 degrees Celsius. Heavier minerals settle to the bottom, while lighter ones float to the top, and crystals begin forming. Beautiful geometric shapes that grow over centuries. Gases dissolve into the magma under enormous pressure, like carbon dioxide in a sealed soda bottle. As more magma enters from below, pressure builds. Tiny fractures form in the chamber walls, creating pathways upward. The magma forces its way into these cracks, heating surrounding rock, which expands and cracks further. Heated groundwater becomes part of the volcano's hydrothermal system, dissolving minerals and sometimes reaching the surface as hot springs and geysers. Back in the magma chamber, convection currents gently mix the molten rock over years and decades, distributing heat and gases evenly. As magma rises and pressure decreases, dissolved gases begin forming tiny bubbles, a process called exsolution. These bubbles grow and merge as they float upward through the magma, like balloons through syrup. The magma becomes frothy, transforming from mostly rock with gas bubbles to mostly gas with rock suspended in it. Gas that occupied 1 cubic centimeter at depth might expand to 100 cubic centimeters near the surface. This expansion pushes magma upward with increasing speed through the conduit, the volcano's throat. The magma can move from less than a meter per second to over 100 meters per second, smooth and continuous like water through a pipe. Near the surface, pressure drops rapidly and gases expand freely. In fluid magmas, the transition is gentle. Magma emerges as lava, glowing red-orange at 700 to 1,200 degrees Celsius. Dissolved gases bubble out peacefully, and lava begins flowing down the volcano's slopes like a glowing river, sometimes just meters per day, other times several kilometers per hour. The lava's surface cools first, forming a dark crust within minutes. This crust cracks as molten lava beneath continues moving, and the glow shines through the cracks in beautiful patterns. The flow advances steadily, fed by more lava from the vent, with thickness varying from less than a meter to over 10 meters. As lava cools, it contracts, creating geometric crack patterns. The most famous are columnar joints, hexagonal columns that form because hexagons efficiently divide surfaces with minimal energy. Each column might be 30 to 60 centimeters across and several meters long, creating natural stone pillars that stand for millennia. These formations appear all over the world, from Iceland's black sand beaches to Northern Ireland's Giant's Causeway, each one a testament to the mathematical precision of natural cooling processes. Escaping gases create holes called vesicles in the solidifying rock. If numerous enough, the rock becomes pumice, so light it floats on water. Some pumice rafts drift across oceans for years, carrying marine life to distant shores and creating floating islands. The rock is filled with countless tiny bubbles, frozen in time, each one a tiny chamber that once held superheated gas. Ground into powder, pumice becomes a gentle abrasive used in everything from stonewashed jeans to toothpaste, bringing volcanic processes into everyday life. Gas plumes rise into the air, mostly water vapor appearing as white clouds, mixed with carbon dioxide, sulfur dioxide, and hydrogen sulfide. A single plume can release hundreds of tons of water vapor daily. As rock cools through specific temperatures, different minerals crystallize in sequence. Fast-cooling lava forms small crystals or even glass, while slower-cooling lava forms larger crystals. The final rock, basalt, andesite, dacite, or rhyolite, tells the story of the magma it came from. Layer by layer, flow by flow, the volcano builds itself over thousands and millions of years. Between eruptions, the volcano rests as the magma chamber slowly refills. This is how volcanoes breathe, slowly, deeply, on timescales spanning years or centuries. The solidified lava begins to weather. Rain seeps into cracks, breaking down minerals and creating remarkably fertile soil. Plants colonize the new rock within years. Heat from below continues warming the ground, creating hot springs colored by dissolved minerals, reds from iron, greens from copper, yellows from sulfur. These mineral-rich waters have been valued throughout human history for their therapeutic properties. Communities have built entire cultures around volcanic hot springs, finding not just physical healing, but spiritual renewal in waters warmed by Earth's deep heat. Circulating groundwater dissolves minerals from hot rock and deposits them in cooler areas, creating ore deposits of gold, silver, copper, and zinc over time. Many of the world's richest mineral deposits formed from ancient volcanic systems. Erosion reveals the volcano's internal structure, layers recording eruptions from thousands or millions of years ago. Each layer is a page in the volcano's history book. Volcanic rocks weather into distinctive shapes. Basalt columns create dramatic cliffs, while harder volcanic plugs resist erosion and stand as prominent landmarks. Most volcanoes form at tectonic plate boundaries. Where plates separate, magma rises to fill the gap. Where they collide, one descends and melts, producing magma. Some volcanoes form over hot spots, stationary plumes rising from nearly 3,000 kilometers deep, creating chains of volcanoes as plates move overhead. The Hawaiian Islands exemplify this process. Through all these processes, there's underlying steadiness. Volcanoes follow physical laws, responding predictably to changes in pressure, temperature, and composition. The drama is just physics on a grand scale, fluids flowing, gases expanding, heat dissipating. Even the most spectacular eruptions follow rules as reliable as those governing falling rain or rising tides. Understanding these patterns helps us appreciate volcanoes, not as unpredictable threats, but as natural phenomena expressing Earth's inner workings in visible, tangible ways. Volcanoes serve vital functions in Earth's system. They release internal heat, recycle materials from deep within, create new land and fertile soil, and release gases that help regulate the atmosphere. What happens inside a volcano is a story of transformation. Solid becomes liquid, then gas-filled foam, then solid again. This renewal happens slowly, peacefully, on timescales dwarfing human experience. The rock beneath your feet was once molten. Mountains grew layer by layer. Soil was once solid stone, broken down by water and time. And deep below, the process continues, patient and eternal, as it has for billions of years and will for billions more.